Alright, previously we have seen in the last class some concepts of flight dynamics, I mean the basic principles and all. We will see later how to derive some equations of motion and then take advantage of this control system design somewhat later. So, we will continue with our generic theoretical development here, and I mean as we know this course is all about modern control design, which heavily depends on this state space representation. So, we will study in one class some ideas about state space representation and then proceed further. Okay. Before doing formal analysis, let us study one or two practical control system examples. When you see a practical control system, you see many components here. Okay. This is a typical temperature control system in a car, where this is your system you can imagine. Okay. And then this is your controller primarily, either a heater or a conditioner or a cooler essentially, and then this is the passenger compartment that you are interested in actually. Okay. Now, you can visualize this system from a variety of subsystem point of view. You are interested in temperature control. So, primarily you need to know what is the temperature inside the passenger compartment. So, obviously, you need a sensor actually for doing that, and you really require some desired temperature, depends on primarily the person who are inside the car. Okay. Sometimes you may want to set a different temperature domain actually, I mean different temperature levels, but that comes as primarily as a reference input. That is what you want to maintain, some sort of a desired temperature. And then there are ambient temperatures and sun, primarily you can think them as some sort of a bias noise or something, but some sensors are also available for finding out what is the outside temperature. So, that information is also available for you. Okay. And then you can also talk about a sun thing, and you can even have a radiation sensor actually. Okay. So, you have a ambient temperature sensor, you have a radiation sensor, you have a temperature of the compartment, that also is measured through a sensor actually. So, various sensors are there, and you can think of as a desired input, that's for your that is what you said actually. There is a control algorithm, there is a heater or conditioner, that is like an actuator, primarily it will excite something for that, for the system. And then you have in various noise input in addition to control input, you can think of that as sun radiation and ambient temperature, and sometimes window opening and closing. Okay, that you can think of as some sort of a random noise actually. So, all these things they go into the system for a practical control system design actually. Okay. So, this is one example. Second example, if you think of is a simple basic flow control example, where you really want to control the water level control in an overrun tank. Okay. Most of our big apartment buildings and all, they do this simple control system mechanism realization actually. Okay. Because many times we cannot observe where the water system, where the water level has gone down, we cannot manually switch it on and things like that. It is not desirable, it is not needed either actually, where a very simple control mechanism can do the job. Now, how is it mechanized? You really want some sort of a desired level in the tank, and then you say there is obviously an outflow depending on your usage and all that. When there is outflow, the level drops, when there is inflow, the level rises obviously. So, you can have a floating device here which can simply measure how much is the height actually. Once you calibrate this device, it will give you what level of the water is available here. And then there is a pneumatic valve which will either open and close. We always assume that the moment pneumatic valve is open, then the water inflow is there. Okay, it is there from somewhere coming actually. Okay. So, then this particular mechanism, you can put that in a flow diagram, something like that. You have a water tank, okay, then pneumatic valve is your actuator. There is a control algorithm mechanism where the desired input comes, actual level is there, and where you measure this, the moment this is falling or something, remember this will have some oscillation, vibration and all that. Okay. So, that will come as a noise to the input actually, noise to the sensor actually, anyway. So, all these things will constitute a control system really. So far we have been bothered about input and output only, but then there are much more details that go inside the system actually. So, what are the things that goes on in a typical system? You can see there is a input, there is output. Okay. But input can be categorized into two sort of input. One is a manipulative input, which is a control variable, and if you see that this is a manipulative input for you, This is also like a desired control and all, I mean whatever control algorithm you are doing and all that, that is manipulative actually. Okay. So, desired level or desired temperature here, these are manipulative variables to the system, okay, that is what you want to do something actually. So, those are control inputs, and then probably like what you see here, these are like there are some non manipulative inputs also. You do not have a control on that. For example, the vibration of this water level, okay, or this I mean ambient temperature, sun and window opening and all that. Those are whatever you consider as non manipulative variables, okay. Those are also input to the system, remember that. There are physical input is going to, I mean the system is going to respond to those inputs, okay, and those are nothing but noise inputs actually, okay. So, you have a control input and you have a noise input, okay. As far as outputs are concerned, there can be two types of outputs. One is the performance output, or this may not be sensed by your sensors, and there is a sensor output actually, okay. So, this is something that you measure by sensor, then take it to the control algorithm, then your control input is computed, then it is fed back to the system. Okay. So, this z what you see here need not be y, it can be same as y, but it need not be y actually in all on applications. So, what you see here, there are two types of inputs, noise input and control input, there are two types of outputs as well, okay. But whatever dynamics goes inside the system, okay, that need not be represented fully by this set of variables. The control, noise, different outputs if you take, there may be still something left out actually, okay. So, that is where the state variable comes, and that is how we define minimum set of parameters, okay, which completely summarize the system status. That's the definition actually. We will see little more detail in the next couple of slides actually. So, we want some sort of minimum set of parameters, using which we will be able to describe the system dynamics in a fairly complete manner actually. Okay. What is the definition? Okay, formal definition is like this. State means like this. The state of a dynamic system is the smallest number of variables. Okay, and these variables are called state variables, such that the knowledge of these variables at some point of time t equal to t0, together with the input variables, okay, for okay, I think this is t is greater than equal to t0. There is a small print mistake here. So, for together with the knowledge of the input variables for t greater than equal to t0, that means you know the knowledge of the input variable for all time after that, then it will completely determine the behavior of the systems for any time after that t greater than equal to t0. Okay. All that you need to know is initial condition of the state variables and knowledge of the control variables for all time. Okay. Then you will be able to know the state variables for any time t greater than equal to t0. After that you know everything about the system. Okay. Remember, typically the outputs are a subset out of state variables in a way, okay, because if you know the state variables, you can compute that compute the output variables as a function of some state variables. They may be directly selected from the set of state variables, or they can be passing through some sort of algebraic function actually. Okay. And also remember that in this definition, okay, the state variables need not be physically measurable or observable quantities. That means, the state variables need not be directly part of these output variables that you are talking actually. They need not be measurable, it need not be part of your performance output either actually. So, what that gives us extra degree of flexibility actually. How do you define these state variables and things like that, so that we can describe the system dynamics completely. Okay. And then the further definitions, we talk about state vector. Okay. So, after these state variables, if you put them these state variables together one by one over the other, x1, x2, x3 like that in a column vector, typically it is defined as a column vector by default. Then you will constitute a n dimensional vector, okay, assuming that you have n such variables x1, x2, x3 up to xn. If you just put them one below the other, it will form some sort of a n dimensional vector. That vector is called as state vector. Okay. And then what is state space? See this, if you consider the coordinates of a system, n dimensional space, which coordinates are nothing but x1 axis, x2 axis, xn axis, then it will constitute some sort of a n dimensional space, and that is called a state space. That is why all these things will see state space analysis, state space representation like that actually. Okay. So, when you talk about let us say R2 space, then you have x1 and x2 in 2 coordinates, that gives you R2 space actually, assuming that these are all real variables by the way. Okay. And then if you have a 3 dimensional system x1, x2 and x3, you can constitute some sort of a 3 dimensional vector. Okay. And remember these all that is required are these state variables are independent, linearly independent of each other, that also satisfies a requirement of a state space. The coordinates needs to be linearly independent of each other. Okay. So, that is but also remember that these coordinates need not be orthogonal actually. Okay. That means, if you take inner product of x1 and x2, that need not give 0. Okay. These x's need not be orthogonal, but they are certainly linearly independent actually. Okay. And also remember that for any dynamical system, okay, the state space remains unique. Okay. That means, if the problem demands an n dimensional space, then it is an n dimensional space. We do not talk about n minus 1 or n plus 1, that remains unique. However, the state variables are not unique. Okay. So, state you can select a different state variable, I can select a different state variable, that is not unique actually. For example, if you constitute some sort of a R2 space, okay, let us say talk let us say this is something like a R2 space, I can constitute let us say x1 x2 here and represent some sort of a flying object by some x1 x2 coordinate actually, depending on where I am flying, I will always find out what is my x1 and what is my x2 here actually, right. However, I can also represent these points by some sort of a r theta coordinate, this is r and this is theta. So, if I represent this thing as something like r and theta, okay, that is also possible. Remember, this is still a 2 dimensional problem. So, whether you talk about this I mean this system, okay, whether you talk about this r theta system or x1 x2 system, the state space is still 2, but the state variables are not unique actually. But there will be conversion formulas available, and we know that actually r equal to the r square equal to x1 square plus x2 square, all sort of relationship, they are algebraically related actually. Okay. And the relationship need not be linear, that is also there, they are uniquely related. Okay. That means r equal to square root of x1 square plus x2 square, that is there. Okay. That is certainly not a linear expression actually. Okay. But anyway, so coming back to that, what it means is the state variables need not be unique actually. And some critical considerations while selecting state variables, first of all they have to be minimum number of variables. Okay. So, in other words, the minimum number of first order differential equations needed to describe the system dynamics completely, you can think of that way. Okay. So, if you talk about number of differential equation all represented by in a first order sense, okay, the number of such differential equations that is needed defines the number of variables that are needed to describe the system completely, and that is nothing but the states actually. Okay. So, that is a primary requirement, you need to collect minimum number of variables. The moment it is more than that, there will be problems actually. Okay. Because if it is less than the minimum number of variables, the thing is you will not be able to describe the system dynamics completely anyway. Okay. Suppose you really require, let us say you really require r and theta, by selecting only r, the theta information cannot be extracted from there. Okay. So, that is a drawback from here. If you select lesser than what is required, you will not be able to describe the system completely. But if you select more than the number of variables required, there can be two issues actually. One issue is computational complexity. That means, if you really require 3 and you have selected 5, then instead of dealing with a 3 by 3 matrix, you have to deal with a 5 by 5 matrix. Okay. That in the sense of A matrix and all that in a linear system, we will talk a little while later actually. Okay. But that is a small problem. The even bigger problem happens to be like if you select more number of variables than necessary, you will lose controllability and observability property, which is even more dangerous actually. Okay. What is controllability and observability? We will see it in a later class actually. Okay. If the system is not controllable, then you cannot design a control system at all. If the system is not observable, you cannot design an observer at all actually, and hence a filter also. Okay. So, in that sense it is more dangerous not only in computational complexity point of view, but with the danger that you will be able to, you will be leading to losing either controllability or observability or both. Okay, that's more dangerous actually. So, that minimum number of variables is a necessary requirement actually. Then linear independence is also required, okay, because if you lose linear independence, that the variables that you select are linearly dependent, then two things can happen. One thing is can be slightly okay, but still it is bad, that is it may not be possible to solve for all other system variables, right. If it is linearly not independent, then you cannot really solve for all other variables actually. But even worse, that is what will happen is it may not be possible to write the complete state equations actually. Okay. So, these are all requirements, because if you see this x 1 and x 2, if the moment I select x 2 along x 1, okay, then theta information is just not possible actually. Okay. I mean this I will not be able to convert it in a proper way, because see x 2 is contains almost the same information as x 1. X 2 does not contain an independent expression actually, information what I mean. So, those problems will start coming actually. So, what you need to remember is minimum number of variables you have to select. Okay. If there is more than that, then there are computational complexity as well as the danger of losing controllability observability. If it is less than that, we will not be able to describe the system completely. And similarly, linear independence is a requirement, because if it is the system variables that you select as state variables are not linearly independent, then there can be a bad issue. That means, it may not be possible to solve for all of the system variables. There can be even more dangerous issue, that it may not be possible to write the complete state equations actually. Okay. So, these are all things to remember actually. Now, how do you select state variables? Typically, the number of state variables, that is the order of the system is defined by that as well, is equal to the number of independent energy storage elements. Okay. That means, if you talk about I mean there are concepts like which of the elements can store energy and which of the elements are passive elements, they cannot store energy like that actually. Can study more details of that in one is probably that is written there. But you can but the unfortunate thing is there are exceptions actually. That means, this need not be a necessary condition basically. Okay. That can simply give you a hint. If you have that many energy storing elements, then that many states are there actually. Okay. Okay. So, is there a restriction on selection of state variables? Yes, we have already discussed about that. They should be linearly independent and they must collectively describe the system dynamics completely. I mean that is we have already discussed about that actually. Okay. Some more details on that you can find in the textbooks as well. Now, before proceeding further, let us see what are the advantages of state space representation. There are several advantages over classical things actually, transfer function what I mean. So, what state space representation gives us is a systematic analysis and synthesis tool for higher order systems, okay, and without any truncation or approximation of system dynamics. Now, whatever may be the system dynamics complexity, either from the order of systems or from the point of view the nonlinearities involved or saturation things involved, whatever it is possible to describe the system dynamics completely using the state space representation without any approximation, without any truncation of the system dynamics. That is why it is a very powerful framework actually. So, most of the things, most of the modern control books and modern control philosophies are based on this state space representation. They normally do not talk even transfer function analysis actually. Okay. And it is obviously a convenient tool for analyzing and synthesizing MIMO system, multiple input and multiple output system. Okay. Remember, there is a transfer function means we always talk about CS by RS sort of thing, which is like single input and single output representation actually. There are extensions to that, where you talk as transfer function matrices, that we will see in the next class also. So, as long as the system is linear, then in input output sense I will still be able to take advantage of transfer function, and I will be still talking about transfer function matrices, that is still possible. But if the moment it is a nonlinear system, I will not be able to do that. Okay. No matter what, this is a very convenient tool for MIMO systems actually, the state space representation. Okay. Third point, it is a uniform platform for representing whatever systems you talk about actually, time invariant, time varying, linear, non-linear, whatever systems you talk about, this state space representation can do the job for you actually. And that is extending that from application point of view, it can describe the system dynamics in almost all systems. You can take examples for mechanical system, electrical system, biological system, economic system, social system, no matter what actually. Okay. Whether the system dynamics comes from some basic physical laws like Newton laws or Kirchhoff's law and things like that, or it is simply simply found from experimental data analysis, which is typically done in biological systems actually, that you carry out several experiments and try to fit models for that. There is no physical explanation, but still the model is capable of representing the dynamics actually. Okay. So, all sorts of things it is possible to describe in the framework of nonlinear, this state space representation actually. Okay. And just remember that transfer function representations are valid only for linear time invariant systems. I have not purposefully put SISO, single input single output, because of that reason. You can still talk about transfer function matrices. However, you can always remember that it is always only valid for linear time invariant system. The system has to be linear system and the parameters must not be time varying. This is a time invariant system, then only you talk about transfer function. Okay. Otherwise, the transfer function representations are not that attractive actually. Now, generic state space representation, let us see, most of the physical systems, by the way, all the examples that are going to follow will primarily confine ourselves to mechanical system, because that is where aerospace engineering falls actually. Many of the examples will fall from mechanical system. However, similar analysis can be done for all these electrical, biological, economic, social, all that actually. So, generic state space, we will talk about let us say state vector, okay, which consists of, it is a column vector, consists of x1, x2 up to xn elements, and all these elements we will assume they are real numbers actually. So, this state variable, this state vector is typically belongs to some sort of Rn, Rn space. Okay. And then similarly, the control input that we discuss, that we account for is u1, u2 up to um, that is a m dimensional space. Okay. And these are also real numbers for physical systems. So, each of them have to be real for physical system, each of them has to be real for physical systems for states also. Okay. So, without further like assumptions of telling all these, by default throughout this course we will assume that state variables, state vector belongs to Rn space, it is n dimensional vector, and control vector belongs to Rm space, that means it is a m dimensional vector. That is implicit, whether we tell all the time or not actually. State vector is a n dimensional vector, control vector is a m dimensional vector, and all of these elements are actually scalar values as real numbers actually. And also one more one more point, that if it is written in a small variable, okay, small letters, that means it is a scalar component. If it is a big letter, it is a vector component. That is also some sort of a notation we will follow throughout this course actually. If it is a big U, that means by default it is a vector. It is a small u with a subscript u1 and u2 and all that, these are all scalar components actually. Okay. Now, if you define like that, the state space representation of the system dynamics of a system in general can be represented something like this. X1 dot is a function, some function of time t. Remember, t is an independent variable, it belongs to R plus only, it is a positive quantity by default again. There is no restriction as such, but we will take time as a positive quantity, and especially some applications we require backward integration, we require some negative information as well actually. Okay. But by default we will take it as a positive number actually. Okay. So, we assuming these system dynamics are always propagated forward in time basically. Okay. So, x1 dot is a some nonlinear function of t, and then all these variables can come in, it can be any function consisting of x1 to xn, and it can also be a function which has this u1 to um. So, some generic function f1, some nonlinear function will represent this x1 dot, and similarly x2 dot, x3 dot all over up to xn dot will be represented by some sort of a system dynamics fn, which can again be a function of t and then all states and all controls actually. So, in a vectorial notation, okay, x dot is nothing but f of this txu. Remember this, when you talk about this f, we will still write small f, okay, assuming that it is still a vector actually. Okay. There are reasons for that. The moment you write big F, there are notations of the vector becoming a matrix really actually. Okay. So, as long as this F is concerned, we will still use a small f all the time actually. Okay. So, x dot is equal to f of t x u, that is the generic function in general, that is the state space representation for any nonlinear system in general actually. Okay. Now, coming to the output variables, okay, we will still again similar to state vector and control vector, we will assume that this is like y is a p dimensional vector, again this by default I will assume that is a p dimensional vector. So, it consists of y 1 to y p is also again a column vector, and all these variables are also we will assume these are real numbers actually, and then these are represented something like this. It is some very close to what is going on here, x 1 dot is something, x 2 dot is like that, but here it is y 1 equal to z 1, y 2 equal to z 2 like that actually. Okay. So, it is actually a p dimensional vector y 1 to y p and given by g 1 g 2 up to z p actually. Okay. So, in general it is y equal to g of t x u, okay, not y dot, remember that. So, it is x dot equal to f of t x u and y equal to g of t x u, and f of t x u and g of t x u are algebraic equations. Okay. So, obviously, the first one is a set of differential equations and the second one is a set of algebraic equations. So, in general state space representation, and mostly we will talk noise free systems, because the noise input is typically ignored as far as control design is concerned, and but that is considered as far as filtering design is concerned, which we will not talk about here actually, like Kalman filter for example and all that actually. Otherwise, these two rely on the philosophy of separation, that you need not talk about noise input directly. In other words, you can design a controller taking I mean assuming is noise free system, and you can also design a filter assuming no control input, and then you can put them together, and that is a separation principle theory and all that, especially for linear systems. If you have a linear system, these two can be proven that you can do that way. Under nonlinear systems also people do that actually. Okay. So, as far as control design is concerned, we will invariably take some sort of a noise free system throughout and see what we can do actually. So, for nonlinear system, that is the form that we have already discussed. Sometimes people write is not g but h actually, whatever you see as g you can write it as h, because this g is reserved for some other thing. I mean, if you talk about something like control affine system, then people talk about x dot equal to f of x plus g of x times u. So, g is reserved for that actually. Okay. So, that is the reason why sometimes people tell no, we will use h actually instead to avoid that conflict. And in general we will talk t does not come explicitly, most of the system you will see that t really not does not appear, unless otherwise you are forced to take it that way. For example, rocket trajectory, when rocket goes up and up, the amount of propulsion that is consumed is huge, and that is typically given in terms of thrust time curve actually, like the m dot mass flow rate time versus time curve. So, in those situations t will come, but most of the time the t does not come explicitly. Okay. Most of the time the parameters remain fairly constant. So, we will not be able to account for this time dependent explicitly, it is not needed either basically. Okay. So, that is a nonlinear system representation, and but when you talk about linear systems, they are mostly linearized system about the some operating point of this nonlinear system, because naturally the system dynamics are nonlinear in general. So, we still talk about linear systems, but remember always that these are linearized system, and we will see one class how to linearize and all that actually, starting from this nonlinear equation. Okay. So, this linear system dynamics is given something like this. Okay, and then this is x dot equal to ax plus bu and y equal to cx plus du. A, B, C, D is given like this actually. Okay. And A, B, C, D are typically corresponding appropriate matrices of dimensions that are compatible. For example, if you see x dot is n dimensional vector, x is n dimensional vector. So, obviously, the A matrix has to be n by n matrix. Okay. Similarly, B has to be n by m, things like that actually. Okay. Now, how do you represent it in a block diagram representation? Okay. This is something like this. Like suppose you take this u. Sometimes in some textbooks you will see bold letters actually, like bold letter means vector, and then non bold letters means scalar and things like that actually. Okay. So, this is like u of t. Okay. Remember this, we are representing this linear system here. So, u we are trying to kind of replicate these two equations, x dot equal to ax plus bu and y equal to cx plus du. Okay. So, what is happening here? If let us construct this x dot, what happens here actually. So, if I start from this integration loop, there is x dot, remember these are set of integrators, it is an integrator sitting there. So, x dot comes component by component, goes out component by component. I collect this vector and then collect this vector as well actually here. Now, once I have x of t, x dot is what? X dot is a x plus b u. So, I will construct x, pass it through a, then add it up actually. So, there is a x component coming here, then there is a b and there is a u, then b u component comes here. So, if I see x dot equal to a times x here plus b times u here. So, that is constructed a x plus b u. Okay. Now, if I consider y is c x plus d u. So, y is here. So, I will pass it through a C matrix. So, that will give me c of x here, and then I will pass this u through d of t matrix. So, I will give me some sort of a c x plus d u representation here. Okay. And in general, remember these matrices a, b, c, d are all time dependent things actually. Okay. So, that is why you see time varying and things like that here. Otherwise, these are, if you can suppress these brackets, this b of t, a of t and all that, you will get a LTI system anyway. But still remember, even if you suppress a of t, b of t, c of t and d of t, you will still be left out with u of t, x of t and x dot of t. These are system variables that will evolve with time actually. Anyways, now that is a philosophical representation of system dynamics. Now, we will see exactly, let us say you start with a differential equation, this let us say it comes from some sort of a physical representation. In other words, for a simple example, you can talk about mx double dot equal to f actually, right, we know that. So, if you have some representation of nth order like that, then how do you represent it in a state space form, and very frequently we will come back to that question and again actually. Okay. So, let us know how to do that. Suppose this is a system differential equation, again y is a scalar and u is a scalar, but still it is given by nth order differential equation in the left hand side. So, because it is nth order, we will really require n system variables, okay, to represent the system dynamics completely, and in a first companion form, which is also called as phase variable form or controllable canonical form. Okay. So, in that sense, what you define is x 1 equal to y, we start in a reverse order sort of thing, then x 2 equal to y dot or dy by dt, we all the way we go to x n, and x n is this person, this quantity, this n minus 1th derivative of the output actually. So, you start with the 0th derivative, first derivative up to n minus 1th derivative. Okay. So, these are something like system variables that will give me some sort of n variables actually. Okay. So, that I will differentiate it and take it through, then what is this definitions here x 1 and x 2 and things like that will constitute something like some sort of a system variable definition, but after that what are the dynamics involved. So, I will differentiate x 1 by 1, let us say x 1 dot actually I differentiate that, then that is nothing but y dot, okay, and y dot is dy by dt and hence it is x 2. Okay. So, x 1 dot, okay, what you see here is y dot is dy by dt and that is x 2 by definition. So, x 1 dot is dy by dt, x 2 dot is d square by dt square, all the way you will find that up to x n minus 1 dot there is no problem. I mean you can just write it from definition, x n minus 1 dot, okay, is nothing but this quantity, right. Okay. So, that way it is easy actually. However, we see the last equation, okay, that will consist of x n dot is d y n the d n y by d t n, that expression actually what you see here. Okay. You have to write it all in the right hand side, okay, and then try to see what all variables they take actually. Okay. Right. So, for the up to first n minus 1 derivative that comes from simple definition, x 1 dot is x 2, x 2 dot is x 3 like that actually. So, x 1 dot is x 2, so that is why 1 here, x 2 dot is x 3, that is why the third column for second row is 1, and then things like that will consist of up to x n minus 1 dot. So, that is all these things are coming simply from definition. Okay. And also along with that 0 0 0 will go here, because the system dynamics does not contain any higher order, I mean any y is not a function of y dot and things like that actually. Okay. Now, coming to the last equation x n dot is all these things you put in the right hand side, and you see that it is a minus a 0 times y, and y is x 1. Okay. So, it is minus a0 times x1, then minus a1 times y dot is x2, like that actually. So, it is minus a0 times x1 minus a1 times x2, like that actually. Okay. So, minus an minus 1 times xn, and then there is a u component here, that is 1 into u. So, it is that last component will come as 1. Okay. So, this will consist of your A matrix. This is x dot equal to A times x, okay, x is here, and this is plus b times u. B can be vector or matrix depending on how many controls you talk about. Be a single control, it turns out to be a vector obviously. Okay. So, and then if you talk about output, and let us say primarily my displacement is what is my concern, that y whatever I have, then y is nothing but x1 only. Okay. So, I will talk about y is equal to x1, but I have to represent in terms of Cx plus du form. Then I will consist this C of x matrix, means C matrix, that way 1 0 0 0 is a row vector here, okay, followed by the same state space vector, okay, same state vector, plus du, and d is 0 obviously here. Okay. So, you got A matrix, you got B matrix, you got C matrix that way. Okay. So, starting from this nth order differential equation, it is possible to write a n dimensional state space representation in this way basically, and that will come back to this I mean idea of representing states variable form from transfer function also in next class actually. There are variety of ways to do that by the way. Now, we will see a variety of examples which will convince us that state space representation is more generic, and it can be possible to write a lot of different systems in a unified manner actually. So, let us start with a simple equation which kind of corresponds to the example that we just discussed. Okay. So, this particular example will be something like this: x double dot plus 3x dot plus 2x equal to u, and I will simply take y equal to x. Okay. In that sense, again going back to the phase variable form, what I will define? I will define x1 equal to x and x2 equal to x dot. I will do it in the reverse way. I will stop at n minus 1th derivative as far as definitions are concerned, because I need n variables actually. So, it is a second order system. So, I need 2 variables here, x1 and x2. Now, when x2 when this differentiation of x1, that is x1 dot is x dot and x dot is x2. So, that will come simply by definition. Yeah. But x2 dot I have to go back to here and then put it in the right hand side, and it is this is minus 2 of x, that is why minus 2 of x1, because x is x1, and minus 3 of x dot. So, that is minus 3 of x2, because x2 is x dot. Okay. So, x1 dot is x2 simply from definition, and x2 dot is minus 2 x1 minus 3 x2 plus u, obviously u is there this side. So, because this is a linear system, I will be able to write it in the standard form, and hence I will put it in a vector matrix representation. I will put the same equation what I see here, x1 dot is x2, that means 0 times x1 plus 1 times x2 plus 0 times u. So, that consists of my first row, and x2 dot is minus 2 of x1 minus 3 of x2. So, minus 2 and minus 3 here plus u, that means 1 u. So, this is my A matrix, that is my B matrix. And what about y? Y is nothing but x, x is x1. So, I will put the matrix C as like this 1 0, x1 and x2 here the same state, and then you have a 0 times u. So, this is your A matrix, this is B, this is C, this is D actually. Okay. So, that is how you construct this state space representation. Again remember that the state space representation is certainly not unique. Somebody can always argue that I will define x1 as x dot and x2 as x in a reverse order, and hence you will represent a matrix representation in a different way. That means, your A B C D matrix will turn out to be slightly different. However, the nice property in linear systems is no matter whatever representation you come up with, they are all similar actually, and nicely they are also tied up by what is called a similarity transformation. We will see that as we go along actually. The different matrix forms, whatever you come up with, they are all tied up with similarity transformation, and similarity transformations preserve eigenvalues, and eigenvalues are poles of the system. That means, the stability nature and all that are not perturbed by whatever way you write actually. So, the system variable definitions can be different, but system properties remain unique actually. That is a nice thing about this type of analysis. Next example, let us be slightly more practical and then talk about a spring mass damper. This is a building block in mechanical systems, by the way. A small components we can always represent in an approximate way by a spring mass damper system. So, very close to what example we saw. This is also a spring mass damper system in a way, but it is more theoretical, but this is slightly more practical because we really talk about a physical quantity for m, physical quantity for c, damping factor, I mean damping coefficient, physical number for k, spring constant, and then there is a control input which is actually coming to the system through some sort of multiplication with b, system parameter. So, this m, c, k and b are nothing but system parameters, and they may or may not vary with time actually, okay. And mostly they, for all practical purposes of control design, for a spring mass damper system especially, we can assume that these variables are fairly constant actually, okay. Anyway, so how do you go about it? You will say again go in a very similar way, you define x1 as y and x2 as y dot, okay, and again come back with these equations that way. So, x1 dot is y dot and y dot is x2 by definition, and x2 dot is all these whatever is in the right hand side, okay, divided by m of course, okay, that is your y double dot, and then you represent it in terms of your x1, x2 variable sense and all that actually here, okay. So, then again because it is a state space, I mean it is a linear system, we should be able to write it in a state space form, okay. So, in general the system matrix will consist of this matrix in general and that vector in general actually, okay. So, that is just an extension of what we discussed in the previous example. Now, coming to little more I mean little more complex system, we can you can imagine this like some sort of a double mass connected by a spring and a damper actually, okay. In a very rough way you can assume these two as some sort of a train compartment basically, in a very rough way, okay. So, there is an engine sort of thing and there is a compartment basically like that way, okay. So, I mean it will consist of n number of such systems by the way, it is not just not one actually, but you can think of that as an engine pulling and then there is something like a spring and damper that connects to the second one actually, okay. So, then this how is it represented? I will assume the track is frictionless sort of thing, and then it will turn out that okay, if I take free body diagrams which is very popular in mechanical system analysis for both M1 and M2, then from the free body diagram of M1 I will be able to write this equation, and for the free body diagram of M2 I will be able to write this equation. And for most of this particular course we will assume that system dynamics are kind of given to us. So, we will not worry so much about how the system dynamics comes from, where it comes, what the physical relationship and things like that. However, we will also remember that these are coming from certain basic principles of nature. Essentially, these are Newton's law, what you see here. Okay. Mechanical systems are primarily they will come from Newton's law actually. So, for M1 I will write the system dynamics from the free body diagram of M1. I am just equating the forces, that is all. Various components of forces I will take, and then there is no particular force that pulls this force explicitly. So, that will become 0, okay. And then there is a particular force that pulls, so that will become f of t actually, okay. Okay, but remember as far as M2 is concerned, the d does not come actually, d comes only to M1 damping factor actually, okay. So, that is embedded in this equation actually. Now, again similar trick, I will define V1 as dx1 by dt, that is the velocity of this M1, that is V1, and then V2 as dx2 by dt, which is velocity of that. So, x1 and x2 define the position of this M1 and M2 at any point of time, and V1 and V2 define the velocities of these bodies at any point of time. So, then I will talk what is my dV1 by dt and what is my dV2 of dt. Remember, these are not independent quantities anymore actually. The way this x2 is coupling here, you see that there is x2 term here, there is also x2 term here, okay. That means, if I vary this force f of t, my x2 is going to change and hence my x1 is going to change, because there is x2 input also coming there actually, okay. So, these are coupled systems basically, and that is why you see MIMO system, even if there are multiple bodies like this, I will be able to still describe them together basically. So, what I am doing here, I am analyzing what is my dV1 by dt, okay. I will represent, I will find that out from this expression, that is my dV1 by dt, and similarly this is my dV2 by dt, okay. So, that is what I will take it to the right hand side. Now, once I do all these things, okay, I will be again able to do this in a state space representation form. So, x 1 dot is nothing but x v 1. So, that is 0 1 0 0. Similarly, x 2 dot is v 2, then that is why it is 0 0 0 1. So, v 2 is the fourth element here. Okay. And also remember, even if you define this variable that way, you have the freedom to put the state vector in whatever order you want actually. That also preserves the properties anyway. You do not have to really write x 1 below that v 1, below that x 2 and things like that. Somebody can always write x 1 below that x 2, below that v 1, below that v 2, that is also possible. But then these entries have to be put in a careful manner. Okay. Whatever way you define, the corresponding elements needs to be put at the appropriate place actually. Okay. So, in this definition and of the variables and this definition of the state vector, I have got this type of matrix here, which is my A matrix and which is my B matrix here. Okay. So, correspondingly look at the equations carefully, x 1 dot is v 1. So, that is why this is a 1, x 2 dot is v 2, that is why this is a 1. However, v 1 dot is like this, whatever you see here. Okay. That is a minus k by m 1 into x 1. So, that is why is minus k by m 1 here, minus d by m 1 is here and k by m 1 here. Okay. But this element is associated with f of t, and f of t is something that we interpret as a control variable. So, this 1 by m 2 will go to the control matrix, actually control influence matrix. The B matrix is typically, by the way, this if you go back to this equations, I mean in general, this is what is called system matrix, this is what is called control influence matrix, okay, and this is what is called as an output matrix and things like that actually. Okay. Anyway, so this is coming back to this, this is what we are discussing. So, this is my A matrix, that is my B matrix. So, these are what you see is starting from a simple linear system. Okay, as long as whatever order is there, we will be able to write it in the form of Ax plus Bu, even if they are coupled together, there may not be only one at a time basically. Okay. If I see this AB matrix, I am talking the dynamics of both M1 and M2 together. Okay. So, I will be able to analyze the system dynamics in a coupled way basically. Now, we will move on to nonlinear things. Okay. Then because we know that state space representation can very well depict nonlinear systems as well. To begin with, I will assume that the same previous example, however, the spring what you see here is actually a nonlinear spring. Okay. Sometimes these springs are designed that way to fasten the response and things like that actually. Okay. So, there are some nice properties of cubic spring equation. That means, if you see this force that is generated here is not a function of linear expression like this, but it is a function of cubic expression. Okay. So, this is what you see here. So, the system dynamics takes the form of cube here. Earlier it was just this with the power 1, now it is power 3 both the sides. So, now you will be able to write this state space equation, but you will not be able to write in a Ax plus Bu format, that is not possible anymore, but you will still be able to write the system dynamics in a state vector representation form actually. X 1 dot is still V 1, X 2 dot is V 2 and V 1 dot is this one which is still valid and V 2 dot is this one which is still valid, but I will not be able to write it in the form of Ax plus Bu form. Okay, but that is still okay, because it is still a state space representation actually. By the way, this example is it is possible to write in the form of f of x plus g of x times u. I mean that is a system like x dot. What I mean is it is possible to write in the form of x dot is equal to f of x plus g of x, which is a matrix, times u. Okay, this is u. Okay, so this is a vector. This is a matrix rather. Okay, that is my u vector actually. So, this is a specific form which is called control affine form and all. We will see it some point of time down the line in this course probably, that there are certain nice properties of that, and then especially in optimal control framework these equations have been studied heavily, but even in dynamic inversion framework these are all certain nice nonlinear system, nice class of nonlinear systems for which we can actually talk about closed form expressions of control design. That means, there will be a formula that will be coming up with the control variable. Okay. So, that is why it is liked, it is studied heavily and all that. But in general, we will be still I mean what we are not discussing that very much here. What we are discussing is x dot equal to f of x u directly actually. So, that is still in this equation what you see here in the left hand side, it still satisfies the need that okay, I can still represent is x dot equal to f of x u that way. Another little more challenging problem, this is something like a ball and beam system, and what it happens here is okay, there is a beam out here which I can tilt it, okay, I can tilt it with angle theta. Okay, it is like a pen which you can tilt it actually, like this a ball beam sort of thing, you can tilt that way whatever you want actually. Then there is a ball out here which will roll along the beam, right, and if there is a hinge out here, the ball is I mean about which the rotation takes place obviously, then the ball will roll to the right or the ball will roll to the left actually, and depending on what angle you are talking here actually. And we will assume the moment of inertia of the beam is J, and these are all other parameters. That means that the mass, moment of inertia, radius of the ball and all that will be assuming that these are known to us actually. Okay. Then if you again go back and carry out the analysis of this dynamics, okay, it will give you some sort of dynamics like this. There is a sin theta angle which will come into picture, okay. Okay. And this definition, all the details I will skip probably. I mean, all that it matters here, it is possible to write the system dynamics of this complicated system completely using state space equation without any approximation. Okay. So, and ultimately it will turn out to be a 4-dimensional system, x1 dot, x2 dot, x3 dot, x4 dot, and this tau is the torque, that is a control variable that I am interpreting here. Okay. That will control my ball on that actually, right. So, using this I will be able to control the system. In other words, I will be able to place this ball wherever I want actually on the beam. Okay. And I can also dance this ball in a trajectory tracking sense, like in what speed it has to go, where it has to stop, where it has to come back and things like that. These are all control objectives probably. Alright. So, the message here is it is possible to write this system dynamics in a complete manner without any approximation. Remember, these expressions that you are seeing here is fairly complex nonlinear equations actually. Sin of x3 is there, x1 times x4 square is there, and here there is x1, x2, x4 term, I mean 3 terms multiplied together, there is a cosine of x3 term, there is x1 square term, all sort of things are there actually, but still it is possible to write and possible to analyze things like that actually. Next example, it is an interesting example. There is a system dynamics where there is a nonlinear expression actually. You can interpret it as a second order nonlinear differential equation of a specific form, okay, and C, K are positive numbers and things like that, and this is actually a small m here, okay. This small m is mass of the system and all that actually, whatever is there. Now, again you go back to this system variable form, this x1 and x2. So, the same standard way, x1 is x and x2 is x dot and things like that. So, state space equation will turn out to be like that. So, what happens here? We are not putting any control thing here, control input is probably not there, but as long as there are initial conditions available to us, we will still be able to propagate the system and all. So, these are called homogeneous nonlinear systems, there is no control input explicitly appearing. Okay. So, this is still a nonlinear system. The problem of this system, the beauty of this system or whatever you can see, if you really analyze this equilibrium conditions and all, that means you have to put these two equal to 0, x1 dot, x2 dot equal to 0 and try to find solutions for x1 and x2. We will see that slightly later also basically. Then we will see that there are not a unique equilibrium point. That means unlike linear systems, linear homogeneous system, the moment you put x dot equal to 0, this vector, entire vector, then x has to be 0 because x dot equal to x plus b u, and u is not there, that means x dot equal to x. The moment x dot is 0, then x is 0, that is the only equilibrium point that you have actually. For nonlinear system, you can have multiple equilibrium points in general, and interestingly it turns out that it actually exhibits a limit cycle behavior, and that is what we discussed in the first equation also. Like if you see x1 and x2 here, x1 and x2 if you plot, it will keep on revolving, okay. And there will be one equilibrium point which is there on the origin, that is an equilibrium point, and unfortunately it turns out to be unstable equilibrium point by the way. So, if it is on the equilibrium point it will stay, but anything other than that it will try to converge to this limit cycle, okay. But once it converges, okay, it will keep on revolving on the limit cycle actually, okay. So, if you really want to do a good control system design, this kind of gives us some sort of a benchmark problem. Because anything other than that will again lead us to the equilibrium, I mean lead us to the limit cycle. From the outside also it will attract, it will try to merge to the limit cycle, inside also it will try to merge actually. Okay. So, if you really want to get out of this limit cycle and go towards the equilibrium point, then your control system should do a proper job actually. That is why these are some of these benchmark problems and all. Okay. All right. The next example is a spring mass as this spinning body dynamics. You can assume that it is a satellite dynamics. That is what the dynamic equations can be represented something like that. Remember, there will be also attitude kinematics which will be coupled with that. That means, the way the satellite is oriented, that will come through certain angles, and those angles can be like Euler angles, can be, there are various representations like MRP, there are direction cosine matrix, there are quaternions and things like that. That part we are not talking here, we are just talking about the dynamic component part of it. So, the dynamic component is given something like this, assuming that these are three equations about the three principal axes. That means, if you take these three principal axes, something like this x1, x2 and x3, okay. This is x1, this is x2, this is x3. Along x1 there is about x1 there is a moment which will be like omega 1, okay. About x2 there will be a moment okay, that is omega 2, like that actually. Then you will be able to represent the system dynamics that way, okay. And remember, this is actually a nonlinear system equation again, because there are double multiplication term omega 2, omega 3 and all that actually. And unfortunately, what happens if you really want to linearize the system dynamics about 0 velocities, 0 angular velocities, the first part of the equation simply drops out actually. That means, you are left out only with this equation, and that is omega 1 dot is this expression 1 by I 1 into tau 1, and omega 1 dot is nothing but theta 1 double dot. If you take theta 1 dot is omega 1, then it is nothing but theta 1 double dot is this 1 into tau 1, and that is essentially something like a double integrator actually, okay. So, these double integrator problems are also available there, but that is only linear expression. So, that may or may not be able to do a job, but the moment you talk about the full system dynamics, this is the equation that you have to deal with actually, okay. So, and linearized system dynamics, linearization trick or linear control system will not be able to do the job because of this. This entire term will drop out actually, okay. You will not be able to even see that actually there, okay. So, these are the various definitions, these are moment of inertia about the principal axis, these are like angular velocity, these are various torques, these are the principal torques that are given to this for control purpose actually. So, it is still possible to write this in the state space form together basically. Remember, this is also a coupled equation, because all of the omega 1 dot is coupled to omega 2 omega 3, omega 2 dot is coupled to omega 3 omega 1, like that actually, okay. So, the effect if you really want to keep, then that is there. Now, you coming to the last example in this series, this is like a real complicated example, airplane dynamics. What you see is a very lot of variables in the left hand side, about 12 equations is essentially, and this is all the coupling that goes on here. If you really want to discuss something called 6 degree of freedom nonlinear model, we will discuss that in a little more detail in one of the classes later. But this turns out that these, if you see these equations carefully, is highly coupled, and if you see that component carefully also, these are all the expressions that you have to deal with. So, linearization is probably may or may not be able to capture all the dynamics completely, and that is where the difficulty comes. So, we want to see this example in a slightly detail later actually. So, that is the message. Can see that various things we can discuss in the framework of this state space equations actually. That is all, I will stop. Thank you.